In this final video for Chapter 5 in Essentials of Meteorology, we're going to talk about two primary precipitation processes, that is, processes in which water droplets and ice crystals grow in clouds. Now, precipitation is basically just any form of water that falls from a cloud and reaches the ground. Okay, so let's start at the very beginning. How do we get cloud droplets to actually grow? Well, the first thing you need is a condition where the air is super saturated. That means the relative humidity is actually slightly above 100%. And then when it does that, the water molecules in the air will be less likely to just bounce off a nucleus, and they'll be more likely to slow down and latch itself onto the condensation nuclei, is what we call this. And these are just bits of dust, aerosols, particles, whatever. Just particles that are suspended up in the air, and water can condense onto these nuclei themselves. So by having high relative humidity or colder temperatures or both, these water molecules are more likely to slow down and latch themselves, in other words, condense onto a condensation nucleus. It's a very effective process, but going by itself, it is quite slow. It would take far more than a day for a cloud to grow enough to produce a storm. Just as a matter of perspective, here is a picture showing a condensation nucleus at the bottom, 0.2 micrometers in diameter, so very, very small. And then when water starts to condense around it, you get a typical cloud droplet of about 0.02 millimeters. That's 20 micrometers or micrometers. Still quite small. And honestly, if we were to depend entirely on the supersaturation and condensation method, we would likely not get very many cloud droplets much larger than 0.02 millimeters. But due to another process which we call collision and coalescence, we can get a typical raindrop with a diameter of 2 millimeters or greater. So let's talk about this topic of collision and coalescence. Basically, what's going on is you have droplets of different sizes that are impacting one another. These two processes are collision and coalescence. Collision means the two droplets actually hit each other. You can think of two pool balls. They come towards each other, hit each other, and if they do so with a high enough force, they break the surface and they collide and become one larger droplet. Coalescence is where you have two drops that are kind of stuck to each other. They're two completely separate droplets, but they're attached to each other. But then eventually they break the surface and they merge and become one larger droplet. Now, when you're dealing with the small cloud droplets, coalescence is not a primary way of growing a cloud droplet. This is because the smaller the surface, the higher the surface tension. That means the smaller the droplet, the more difficult it is to break through the surface of that droplet. And so since it's hard for small cloud droplets to coalesce because of the high surface tension, they depend primarily on condensation from the supersaturation, which was the first thing we talked about. And they also depend a lot on collision. Over time, droplets will get larger, and when they are larger, these droplets will start to fall through a cloud. As they do, two things happen. One, a number of droplets will actually collect on the front side of each droplet. They do kind of merge, but they don't actually coalesce and turn into one droplet. These just kind of hang out where they are until the droplet gets bigger and forces it to coalesce. What's more important in this case is that as the droplet falls, smaller droplets are pulled into the droplet's wake, the large drop's wake. And as it does that, these small droplets collect on the backside of a raindrop, and there it is much easier for them to coalesce, and that is where the primary growth happens in the collision coalescence process. How large can a droplet get? Well, that depends on what we call the terminal velocity. The terminal velocity is the maximum fall speed due to air drag. Large droplets will have a higher terminal velocity because they're larger, gravity's going to pull them faster, so they'll be able to go faster. But smaller droplets, because they're lightweight, are more easily picked up by air, and so they have a lower terminal velocity. So what happens is if you have a small droplet which has a very small terminal velocity, any small updraft is going to take that droplet and push it up higher into the cloud. As it does so, it's going to undergo collision coalescence and grow until it is a larger droplet when it's going to have a higher terminal velocity. So as long as you have an updraft that can sustain these larger droplets, the cloud droplets will stay in the cloud, growing and growing and growing. As soon as this droplet is too large for the updraft to actually hold, it will start to fall, undergoing more collision and coalescence on the way down, until you have a full-size raindrop coming out of the bottom side of the cloud. The end of chapter 5 talks about many different types of rain precipitation. But precipitation isn't always liquid water. Sometimes it has to do with solid water. So let's talk about the second precipitation process, which we call the ice crystal process. Now, most clouds are really a combination of water droplets and ice crystals. But especially when there are a lot of ice crystals around, the air is very cold and the water becomes what we call supercooled. That means that the temperature is actually slightly below freezing, but it's still in a liquid state. Now, the key is that the saturation vapor pressure around water tends to be higher than around ice crystals, which means you can have more water vapor kind of hanging around a liquid water droplet. And since there's less water around an ice crystal, then you're going to have water droplets moving from the high saturation vapor pressure area around the water droplet to the ice crystal on the right. And so the ice crystal ends up growing at the expense of the water droplet. And once the water vapor is right around the ice crystal, it freezes onto the surface, causing the crystal to grow. Then, when the crystal is large enough, gravity takes over and starts to pull it downwards. As it hits more droplets, the droplets will impact the surface of the crystal and freeze onto it, causing the crystal to grow even larger. This is a process called accretion. But there comes a point when the crystal becomes too large. When it does, the crystal becomes unstable and fractures into so many tiny, tiny crystal pieces. But there's still an attractive force between all of these ice crystal pieces, so they aggregate together. That means they are attracted to each other and the crystals recombine in some different crystalline pattern that allows it to actually fall more easily without fracturing. So this is the process of accretion and aggregation, and is the primary method of growing ice crystals. The end of chapter 5 also talks a lot about different types of snow precipitation, as well as ice precipitation, such as freezing rain, sleet, and hail.